Sure.
Hello, everyone. Welcome to the first session of ITE seminar this semester. Today, Lisa Lee will be presenting her master's thesis work on navigating the transit network, understanding riders' information seeking behavior using trip planning data. Lisa Lee is a MASc student here at University of Toronto under the supervision of Professor Amer Shalaby. She is interested in how emerging data sources can be used to improve public transportation and promote sustainable cities. Lisa received a BSc in Civil Engineering from the University of Toronto in 2019. She is currently working at GHD, where she is focused on pedestrian modeling and movement analytics. The presentation will be around 40 minutes, followed by questions and answers. So Lisa, the floor is all yours.
Great, thank you. So here's just a quick outline of what we can expect to hear today. And I'll kind of just jump right into it with the background and motivation of the study. So over the recent years, there has been a lot of focus and attention placed in improving public transit and encouraging a modal shift away from private vehicles and towards transit. So a fundamental aspect of having a successful public transit system is really to increase ridership. Therefore, in addition to expanding transit infrastructure, agencies have also been investing heavily in providing information to travelers both before and during a trip to improve the quality of their experiences. And providing information to transit users is really important as it informs them about all the available options before making a trip, helps people reach their destinations in a timely manner, and also helps to overcome possible disruptions along the way. Furthermore, the advancement of digital technology over the last 2 decades has really allowed for the emergence of new sources of information. With the widespread use of smartphones, travelers now have easier access to information such as route timetables, detailed itineraries, and estimated vehicle arrival times. So as a result, information provision has really played a more prominent role in how people undertake transit trips. So there has been a limited study, however, investigating information seeking behavior through the observation of actual choices made by people. Many previous studies have been based on data collected from surveys, which has some limitations. So firstly, surveys can be costly to conduct, and they may lack generalization due to issues related to sampling and response rates. Another limitation of this method is that individual responses may not always correspond with their actual behavior. For example, recall error can occur when participants are asked to describe past experiences. And with stated preference surveys, respondents are given hypothetical questions that may differ from how they behave in real life. So related to this is the fact that surveys are often conducted at a single time point. So it's difficult to collect information about unexpected events such as a major disruption. And it's also difficult to understand how people's information requirements might evolve over time and how they react to sudden changes to the network. Finally, from the literature, it was quite apparent that the study area and context plays a very important role in how people seek information, as people from different regions were found to have very different behaviors. So with that said, most of the research was found to be conducted in Europe. So it's interesting to see how travelers from North America and Canada specifically might differ. So therefore, the study proposes an alternative approach to understanding the role transit information plays by using retrospective itinerary searches made by people in Calgary over the span of 6 months. The motivation behind this is that we can better understand the need for information and how it changes dynamically. And the finding can also help improve communications between agencies and travelers. Lastly, understanding this can provide further insight into people's revealed travel behaviors, which can in turn be used to develop more accurate travel demand models. So for example, information provision has been shown to influence people's mode choice, departure times, and route choices. So it's an important aspect. So from this, we kind of developed 2 main objectives that we wish to address. And the first objective here will mainly be investigated through data exploration, while the second objective will be addressed through statistical models. So the trip planning data used in this study comes from Transit, which is a smartphone app that provides real-time public transit information across 200 cities over the world. The app contains several features here, but for this research, we'll only be using trip planning feature, which provides users with sort of detailed itineraries of how to reach a destination. The backend data from the app, other features are not included in the scope of the work. So the geographical area used in this study is Calgary. Calgary has the fourth largest public transit system in Canada, and its network is comprised of 2 light rail transit lines, shown here in the red and the blue line, which is connected to quite an expansive bus network. And the data covers the study period of September 3, 2018 to March 2nd, 2019. And during this time period, Calgary Transit actually underwent a major network overhaul where 3 new buses were proposed, 3 new bus rapid transit lines were proposed, shown in the orange, purple, and teal lines here. And along with this BRT system, they also made 35 other changes to routes where they were either added, modified, or discontinued. And upon the opening of this new network, there was found that there was a lot of reports of confusion the following day. And this is sort of indicating that there might have been some time required for people to become accustomed to the system again. So therefore, this also provided us with a unique opportunity to investigate how a drastic change in the network might influence people's need for information. So here's an example of what the data provided by Transit looked like. Each of the record contained a unique user ID, which was linked to the smartphone device. And we also have a timestamp of when a search query was made by the user, as well as the locations of their origin and destination trips, which was specified by the user. So the itinerary searches included in our analysis were only confined to those that began and ended in Calgary. And during the data cleaning process, it was found that some of the users will make multiple searches of the same locations within quick successions. So this was likely because they were rechecking their itineraries. And to account for this, we kind of removed searches made within 10 minutes of each other that were identical. And another thing to note is that although the app allows you to sort of specify your departure time or arrival time and plan for trips in advance, this information was not documented in the data space at the time. So to learn more about the general trip usage patterns, an explorative analysis and visualization was conducted. So here we have the daily number of itinerary searches made during the 6-month period, and it was compared against the observed passenger boarding counts that was provided by Calgary Transit ABC data system, so to identify any similarities and differences between the two. So it's quite evident that the number of trip searches made is lower on weekends, as you see sort of like a cyclic cycle. And this is also true in the APC count. And then there was also a significant reduction in app usage observed during the winter break period. And this also was true in the transit demand. So what's interesting is there is a sudden spike here seen in the trip planning data usage that occurred on November 19th, and this corresponded to the opening of the new BRT lines. So we see that there isn't an influx in transit riders on this day, which makes it very likely that the increase in searches was a direct result of the network overhaul. And moreover, as you see that as time goes on, the number of itinerary searches kind of reverted back to regular levels, indicating that people might have been getting reacquainted with the network again and no longer needed the aid of a trip planner. So we also looked into the frequency of app usage for the people using this using transit app. So we see that in general, the frequency plot reveals that while most people made searches less than 5 or less searches, there is a substantial number of people, so approximately 17%, who are quite reliant on the app and the information that it provided them with. And transit demand is also known to fluctuate greatly throughout a single day. So we would assume that itinerary searches would also do the same. So here's a temporal profile of both the data sets. And overall, the number of itinerary searches exhibit sort of a similar bimodal distribution where the peaks coincide during the evening and morning rush hour periods. And we see that the weekend patterns are also quite similar between the two. However, when you compare the itinerary searches, you see that there's quite a lot more midday trips happening and searches happening, and that the evening period is greater and wider. So this disparity could indicate that perhaps there's more discretionary trips, such as people going shopping or visiting friends, that are typically made during these times. So the spatial distribution of itinerary searches was also investigated to see which areas saw a greater volume of app usage and where people were most interested in traveling to. The map reveals that during the AM period, people were mainly searching to go to these three hotspots, which correspond to downtown core, University of Calgary, and Mount Royal University. This may suggest that app users are mainly using it to commute downtown or are students. And what's also interesting is that there's a lot more search activity happening in the northern part of Calgary compared to the south. For the midday, the pattern is a bit different as it's mainly dominated by searches made between these three areas as opposed to from the suburbs. The PM and evening period of the spatial maps kind of mirror the AM period, where it's now more of the searches that start either downtown or by the universities are going back to their suburbs. This is very typical of commuting patterns. However, this pattern is seen to occur even into the evening period, which may perhaps suggest that people do not go home immediately after work and they take smaller trips in between. Overall, these visualizations indicate that while itinerary searches display a similar pattern to transit demand, there are some differences between them, and this might suggest that specific circumstances and factors might drive people to seek out information more often than others. So the next part of our analysis is to perform a cluster analysis. And clustering is an unsupervised machine learning method commonly used to reveal hidden patterns and data groupings. So as mentioned, we will first cluster the search records and then the users. For both of these, we used the k-means algorithm, and this was mainly due to two reasons. Firstly, it's really popular and used in many applications, including transportation research. And secondly, it's simple to implement and scales well to large data sets. So here's just a quick rundown of how the algorithm works. And the main challenge with and disadvantage of the k-means algorithm is deciding what this k value should be, as it can change the results quite drastically. So one common strategy is to use the elbow method, where the sum of squared errors is calculated for a range of k values. And then the optimum number of clusters occurs when the gain in reducing this error begins to diminish, because at that point, data is being overfitted. So the first clustering analysis involved using individual search records. So our first step was we had to first create variables or features to identify these. These variables were chosen because they were believed to be important external factors that may influence people's choice in using a trip planner app. So one thing to note is that travel time, travel distance, and the number of transfer required wasn't something that could be directly attained from the data set. So instead, we had to estimate it using OpenTrip Planner. So transit app search records were used as input parameters into OpenTrip planners, which would then in turn return detailed transit itineraries of how a passenger would get to their destination. And this included the travel time, distance, and mode for each leg of their journey. And finally, since the k-means algorithm relies on measuring the distances between points, the feature was scaled so that every feature has equal weighting in the algorithm. So 6 clusters were ultimately identified from the elbow method, and the plot and table shows the average values of features within each cluster, and this will help us with defining the groups. So the values highlighted in gray kind of indicate when a feature seems to stand out amongst the groups. So for example, clusters 3 and 6 were both kind of characterized of having longer travel times and distances as well as more transfers. So we might say that these clusters are used to describe itinerary searches made for longer distance trips. So based on that last slide, each of the clusters was given a description, as you can see. And some interesting points to make out is firstly, about 75% of searches were classified as being short trips. So while this may seem counterintuitive that shorter trips or simpler trips are more frequently searched for, one possible explanation for this is that people are just simply less likely to use public transit for longer trips, and therefore they don't look up the information. Likewise, cluster 1 and 6 have the two smallest groups, and these were searches that started further away from a rapid transit stop. So this could be that when there is no rapid transit option available, people are less inclined to use public transit altogether, and therefore this results in fewer searches being made. So a temporal distribution of the number of itinerary searches made on average was also created for each of the clusters. So clusters 1, 2, 3, and 4 both have kind of typical commuting patterns that are of a bimodal distribution. But cluster 5 here we see is quite unique in that there's significantly more itinerary searches being made during the weekday evening rush hour period. So referring back to the description of the group, it is plausible that this temporal pattern is observed because there is discretionary trips being made after work. So it's quite reasonable to understand that when the weather is nice and people are more willing to partake in activities such as like going out and meeting with friends. The temporal plot for cluster 6 is also quite different from the others. It also has a unimodal distribution with a peak that occurs during the morning rush hour this time. So one explanation for this is that people in this cluster want to be on time for work in the morning. And because their trips are longer and start further away from a rapid transit stop, there's more uncertainty involved in them, so they want to search it up first. Lastly, for this section, we also visualize the spatial distribution of trip searches within each group. Itinerary searches made in clusters 2, 4, and 5 all occur kind of between the downtown core and universities and a commercial district. And these clusters all have a similar trait in which they were classified as short trips that originate near a rapid transit stop. Only with cluster 1 do we see a distinct spatial pattern amongst the clusters of shorter trips. And this is expected because within cluster 1, it was trips that are further away from a rapid transit stop. However, it's also, again, interesting to note that most of the search activity happens in the northern half of Calgary. So this difference might indicate that there's some sort of built environment discrepancy or transit network differences in these two regions. And then cluster 3 and 6 were both defined as searches made for longer trips, and they also have a distinct spatial pattern. So cluster 3 seems to contain more trips occurring between suburbs, whereas in cluster 6, we have trips that appear to focus from the outer suburbs down to into the downtown core. So in relationship to the temporal graphs, the majority of itinerary searches from cluster 6 occur during the morning rush hour, which might support the idea that this is used for serving commuting trips. So now the next part is using unique user IDs to profile different transit app users and investigate their their search habits. So to conduct this analysis, each user ID was assumed to represent a single person's activity, and it was grouped together. And this time we included variables on that indicate like how regular of a user they are, such as the total number of searches they made and the number of days that they checked with the app. We also calculated their usage rate during different time periods. So for example, their AM usage rate was defined as being the total number of searches they made during the weekday between 6 a.m. and 9 a.m. divided by the total number of searches they made altogether. So this was also repeated for the midday, PM, evening, and overnight period, as well as weekends and holidays. So as before, we plotted the values to kind of visualize it and infer different types of users. So it's apparent that most of these clusters are dominated by a single time period of heavy usage. So for example, this orange bar in the graph shows that a lot of people in cluster 2 primarily make searches during the AM period. Upon further inspection, this result was found to occur because many of the people who make itinerary searches don't search them very often. Therefore, if a person only looked up a single trip query on transit app during the AM period of the study, they will be classified as someone who primarily seeks for information during the morning rush hour. This is also demonstrated by the low average number of itinerary searches and days spent using the app. However, there's still something that we might gain from this. So firstly, clusters 2 to 7 were found that the largest out of these ones, the largest proportion of users come from cluster 3, which corresponds to users that primarily make searches during the midday. And this seems to suggest that amongst all the infrequent app users, people seem to require transit information the most during midday. So one explanation for this is that trips taken during the AM and PM peak period are more likely to be commuting trips in which a user may not need to consult with an app as they're familiar with these trips already. The largest group was cluster 1 and accounts for about 1/3 of users. And this cluster was quite unique because people within this group were found to make itinerary searches for all time periods. So furthermore, it seems like these people are more regular users because based on the average number of itinerary searches and days checked using the where they check the itineraries. And then the temporal profile of clusters also resembles transit demands. So users in this cluster would consult trip planners over the weekend as well. So this might tell us that people are more reliant on public transit, which may also explain why they use the app more frequently. So a lot of the previous studies have found that people who use transit more are also the ones who seek out transit information the most. The last part of this research involves estimating a statistical model, and this is really used to answer our second objective. Here we decide to develop a panel data model, which contains repeated observations on the same cross-sectional unit over a time. So the advantage of this is that it really contains more information than a pure time series or cross-sectional analysis. And the unit of analysis chosen for the study was the traffic analysis zone level, which is traditionally used in transportation planning and travel demand modeling. With regards to the time dimension of the panel data set, an hourly resolution was chosen to model temporal dynamics as accurately as possible. And as a result, we have the number of transit itinerary searches originally from a transportation analysis zone, and that was our dependent variable in the study to represent travelers' desire for transit information. So this is based on the general assumption that when there's a greater demand for transit information, more itinerary searches will be made. The dependent variable for one observation was counted by adding up the total hourly number of searches conducted within each TAZ when no itinerary searches were made within a TAZ for the duration of that hour. The dependent variable for the observation was simply set to 0. So the transit app data was also combined with other data sources so that we can create other variables, as it is assumed that itinerary searches would follow transit demand patterns to some extent. It was important for us to control this in the model so that we are measuring the effects of factors irrespective of transit demand. Therefore, the APC data provided by Calgary Transit was used as a proxy for transit demand. The data source was also used to derive an indication of transit reliability. So to measure this, the average on-time performance, which we define as being 1 minute early or 5 minutes late of a vehicle within a TAZ over a given time period, such as the AM peak, was calculated using this APC data. So the general belief is that zones of higher on-time performance would require fewer searches to be made compared to zones of less reliable transit service. So we also use GTF static feeds to obtain some additional variables to relate to the transit network, and historical weather data was also merged into the data set. And while social demographics were found to play a very important role in determining people's likelihood of using transit information, we did not have information about this from the users. So instead we had itinerary searches had to be kind of compared to what census attributes at the zonal level. So here's the final structure of what the panel data look like. And as you can see, each zone basically has an observation for every time step. So when it comes to developing our model, something to consider was that our dependent variable was account data. So it takes on non-negative integer values. The data also had a positive skew and a large number of zero values, suggesting that the residuals are not normally distributed, making it inappropriate for ordinary least square regression. So to address this, generalized linear models have been developed to allow for non-normal error distribution. A common one being the Poisson regression, where the log expected value can be expressed as a linear combination of the independent variables and a set of unknown parameters. The dependent variable in this case will follow a Poisson distribution. The main disadvantage of this is that the Poisson regression assumes that the mean and the variance of the data must be equal, which is not usually true in real life. So therefore, an alternative to this is the negative binomial regression. So with that being said, those were techniques kind of used to model cross-sectional count data. But what about with panel models? So the general form of a linear panel model can be expressed like so, and in our case, Y can represent a vector of hourly itinerary searches made within a TAZ at time t, and X is a matrix of the independent variables, beta is a vector of parameter estimates, and we also have an error term here. So what makes panel models a bit different is that it has additional parameter that represents individual specific effects. So these specific effects can vary across TAZ and over time and be treated as random or fixed. So the three most common methods for linear regressions with panel data are pooled estimators, random effects estimator, and fixed effects estimators. And these approaches can be extended to the Poisson regression and for the most part, the negative binomial regression. So the pooled estimator is the simplest approach and basically ignores the panel structure of the data. However, since the pooled estimator does not include the individual specific effects in the model, these effects become grouped into the error term, and this can lead to biased results. The random effects estimator assumes that individual effects are distributed independently of the regressors to account for unobserved heterogeneity across individuals and time. So here, the individual effects are a random variable. So for example, it may follow a gamma distribution. So this method is more efficient when the individual specific effects are random. But however, if there's correlation between the effects, the specific individual specific effects and regressors, it no longer produces consistent estimates. So in that case, we might want to consider a fixed effects estimator, which assumes that individual effects are constant. So one method of attaining a fixed effects estimator for account panel data is to run a Poisson regression with the addition of a dummy variable for each individual -1 in the data set. So doing so allows any heterogeneity amongst the individuals caused by omitted variables to be explicitly estimated in the model. And we can also add in dummy variables for seasonal variations to control for any zero correlation across time. So one thing to mention is that while there is a fixed effects negative binomial regression, it's not actually a true fixed effects estimator. And the main drawback of the fixed effects estimator is that the parameters for time invariant variables cannot be estimated in the model, so these effects cannot be studied. So ultimately, the choice between the fixed effects or random effects is not always straightforward. While the Hausman test suggested that the fixed effects is more appropriate for our data set, we couldn't see the effects of variables that were constant throughout our time period. So therefore, we will instead present two different models for comparison, fixed effects Poisson regression, as it's very robust, even under the presence of overdispersion, and it controls for omitted variables. And we'll also compare that to the random effects negative binomial model. So here are the results of the two models. Since the number of trip searches was expected to be proportional to actual transit demand, we used the log of hourly passenger count within a TAZ as an offset variable to model the counts as rates. And therefore, the parameter for that was constrained to 1. When it comes to interpreting results, we'll focus on the significance and the effect size of variables. And in this case, the effect size represents the change in mean trip searches for a unit change in the independent variable, with all else being held constant. Sorry, the percent change. Both of these models tell a similar story. However, we do see that the effect size of the random effects negative binomial model seems to be generally smaller. The first thing to note is that the reliability has a strong negative effect on the number of itinerary searches. This means that when the on-time performance is low, you can expect higher number of itinerary searches being made. So this is an important finding because it also suggests that reliability or lack thereof is not something that's noticed by riders and they adjust their behaviors accordingly. For the next variable, we interestingly see that the number of active transit stops operating within a TAZ does not have a large effect on the number of trip searches. With regards to weather condition, we see that while temperature does not have a very large effect, precipitation does. In this case, we see that for every millimeter increase in precipitation, we can expect average trip searches to increase by 25 to 28%. And this could be due to two reasons. Firstly, people want to time their trips better to avoid having to wait in the rain or snow. And secondly, rain and snow can both cause unexpected delays to a trip. We also see that the introduction of the new MASc BRT lines caused a significant increase in trip searches. So this makes intuitive sense because the network underwent a drastic change and routes were altered. So it's likely that there was some confusion on how to navigate through the new network and people had to rely on trip planners more. However, we also saw that the occurrence of a service disruption is seen to have an even greater effect. So this data was, so this variable is created from using past tweets from Calgary Transit that indicate when there was a severe LRT disruption. And we found that in the fixed effect model, that unexpected delays increased searches by 80.6%. So it's very expected for people to seek information in this scenario, however, because with a trip, especially with a trip planner, because travelers want to find alternative routes to reach their destination while they're being stranded at a station. The variables that did not change over the course of the study could only be investigated using the random effects model. So in terms of social demographic factors, both of the median household income and the percentage of visible minorities were found to be statistically significant. However, the effect of these two factors were quite different. Income was observed to have a very minor impact in itinerary search rates, whereas a 1% increase of visible minorities residing within a TAZ has a 35.8% decrease in the number of trip lookups. So this result was initially surprising because low-income households, visible minorities, and immigrants tend to be more frequent users of public transit. However, a possible explanation for that is that people who use public transit regularly may require less help from a trip planning tool than infrequent riders. And another reason could be that these people have lower accesses to mobile devices and cannot make searches. We also looked at how people's trip planning usage is impacted by time of day and day of the week. So we created an indicator variable to compare holidays and weekends to weekdays. And you see in the fixed effects model, there is no significant differences between weekend and weekday app usage. However, this is not true in the random effects model. Nonetheless, though, the units of transit app is seen to be higher on holidays, and this could be due to the fact that people are more likely to make unfamiliar trips on holidays, and also because transit schedules tend to differ on holidays. And we also looked at how people's information seeking behavior changes throughout the day. So the reference time used here is the AM crown period, which is defined as 7 to 8 a.m. And interestingly, we see that more trip switches were made during the midday and in the PM and evening period compared to the AM peak. So a possible reason for this is that people may be taking more discretionary trips and unfamiliar trips during the midday and after work before heading home, and therefore need to consult with trip planners more. So the results of this suggest that people are more likely to use trip planning tools for discretionary trips, as a significant number of searches were made during off-peak hours. This is also inferred in the cluster analysis. For example, cluster 5 had a temporal profile that did not match with typical commuting patterns. Furthermore, the cluster analysis found that most of the searches made are for shorter distance trips and trips that are located close to a rapid transit stop. So this leads us to believe that while more complex trips are likely to benefit from the use of trip planning tools more, people tended to dismiss using transit altogether in these situations. It's also very evident that people seek out information during times of uncertainty. This was seen in the model as the reliability of the service, the occurrence of a service disruption, and a drastic change in the network all had very large effects on the number of trip searches made. So based on this finding, we really want to emphasize and recommend the importance for agencies to communicate to travelers during a disruption. This includes providing information through multiple sources as well, such as in-vehicle announcements on social media and on official websites, because not every traveler will have access to trip planning apps or be using it. Furthermore, transportation operators should also be prepared to increase communication levels during instances where transit service is expected to be deviate from its regular schedule or service, such as during planned maintenance closures and large concerts or sporting events. Following with this idea about how people may not be using trip planning tools, the agencies should also be careful about the digital divide. So while smartphone apps like Transit have generally made it easier for riders to access information, there's a group of people who cannot afford to or use smartphone to access this public good. Therefore, and this is particularly an issue because individuals from this vulnerable group are also those who are more likely to rely on public transportation. So the negative coefficient signs for visible minorities in the model suggest that this may be happening and that's something that should be investigated in future works. Lastly, one possible future application of trip planning data is to use it to help agencies identify where there's a demand for transit. So during the study, it was interesting to note that there was instances where trip searches were greater than the APC data, or there were trip searches being made in areas far away from any transit service. So this may suggest that there is a desire for transit in those areas. Finally, I'd just like to acknowledge Calgary Transit and Transit app for providing the data needed to conduct the study and their support in it. And I'll also like to thank Professor Shalaby and Professor Farber for their support and guidance throughout this journey. Thank you, and if anyone has any questions, I'll be happy to take them.
Thank you, Lisa, for such a great presentation. Interesting work. So the floor is open for questions.
I can get the ball started unless you're seeing some questions coming in from the students who I'd prefer to hear from first.
No, I don't see any questions. Yeah, so you can start.
Okay. Okay, great. Lisa, congratulations. It's been wonderful working with you over the last couple of years and seeing the evolution of this project has been really, really exciting for me to be a part of it, and you've done a great job. I have a question to, I mean, it's not about this research that you've conducted, but I have a question like this. If you were to be able to conduct some kind of survey of the transit app users, I'm wondering what kind of information you would try to obtain from the users and what you would do with that.
Yeah, so I think the biggest disadvantage of using this sort of data set is that we don't have any sort of knowledge of what the user is, so like who they are. So I think what surveys kind of excel at is that they do get those social demographic variables that we can. So this data set, there's definitely a disconnect between that. So while we're able to capture their behavior really well, we don't know who the users are. And I think if we can combine that, that'll bring a much greater insight into this, because then we can see specific user demographics and how they behave differently from others.
And anything other than user demographics along the same line that you would like to explore?
I think we can even get information about maybe their like perceived ideas about public transit, their perhaps like history of using transit, and such. And maybe even like where they're going to, or sort of their trip activities or trip purposes.
Yeah, I guess more of a comment. I mean, I agree with you on all of those things, but I think another opportunity is to actually ask the users whether or not these are routine trips, or actually ask them why they used the lookup for that trip, right? Maybe they could tell us, oh, it's bad weather, there was a disruption, this isn't a trip I normally take, or I'm just nervous about being late. Like, I think it would be really interesting to dig into some of their stated ideas for why they are seeking that information, because that could like really confirm a lot of your explanations that you have that are reasonable and rational, but unconfirmed.
Yeah, that's the big thing. A lot of these are just based on sort of inferences for what we see. So being able to validate that would be very useful.
I think we have two hands raised. So Brandon raised his hand first. So please go ahead.
Lisa, this was really interesting. I've been trying to encourage my academic friends to do more research on the impact of customer information, real-time information apps. So this was really interesting, very dense. I'm trying to think it through. I think it would be worth parsing it a little bit to try to draw out those conclusions a bit more. I guess I had a question, and I think I know the answer, but a lot of the inferences were very interesting, but the one I didn't quite see specifically was the actual some sort of correlation or looking at the impact of headways. In other words, in terms of, you sort of inferred it by sort of saying, oh, well, in the evening, there's, frequencies are lower, but it probably was not possible, but to correlate your data to the actual frequencies of the routes that they were exploring. I was just curious what you thought about that.
Yeah, I think that was actually a big limitation to this. So we did account for transit reliability, but we had to use sort of on-time performance. And even then it was kind of estimated in sort of a crude way where we didn't have every vehicle. We only had it during when there was a stop action recorded. So definitely if we had information about headway regularity, I think that would be even more insightful for this and seeing how that might relate to people's app usage patterns.
Yeah, I was just not just thinking about regularity, but actually the the length of the headways. In other words, I mean, one can hypothesize that use of real-time arrival information should increase with the as headway increases. If you're waiting for a 30-minute bus and you miss it, the impact is much greater. But I'm not quite sure about whether trip planning works the same way. I mean, that's sort of another issue about trip planning versus just real-time arrival information. But it's all very interesting. Thank you.
Yeah, I do have to say that there have been studies where they've used surveys to ask people about when they look up trips, and there was a lot of people who were more like metro riders said that they didn't do that because it wasn't an important factor for them to consider.
Right. I mean, I've seen studies like Kerry Watkins was one of the earlier ones on intercept studies, sort of estimate the perception of wait time with or without real-time information. But this gets in, and you were looking at the demand, and there's a lot of other information in there. Thank you.
Professor Amer.
Thank you, Lisa, for the presentation. Again, it was really a pleasure having you over the past 2 years. It's great work and very unique. I'm actually quite intrigued by your observation where certain areas or certain TAZs that really recorded trip searches, but didn't record any APC activity. So can you elaborate on those a little bit? Where in Calgary did you find those areas? I know you excluded them from your study, and you made a comment in the end that this might actually give some indication of where public transit might be needed. So maybe if you can just elaborate on this a little bit.
Yeah, so I do admit I haven't looked into this in great detail, but I recall I did a sort of a quick visualization. It was sort of on the boundary areas, so that might be something to do with why there wasn't transit reaching those areas, but people were still interested in taking transit trips.
Yeah.
Lisa, Amer, can I just, it may be also that people do a search and then decide that it's going to take too long and they hop into an Uber.
Yeah.
Yeah, it wasn't in the study, it was really in the literature, it was found that people kind of already have an idea of what sort of modes they want to take, and people just dismiss taking transit for longer trips. Like their default would be to drive. So I think that's a big reason why we saw a lot of shorter trips being made from the app compared to longer trips.
Yeah, actually, there's a question in the chat box by Ala, which also I was thinking about. So what's the percentage of users that did those searches?
Sorry, which kinds of searches?
In areas that there was no APC activity.
Oh, that I don't remember off the top of my head. Yes.
Can I have one more quick question from Willem?
Hi, Lisa. Yeah, thanks. Great presentation. I was super interested and curious about your cluster one. I got really excited about the map you put up from that cluster one, and that you identified these. If I remember correctly, it was long trip searches far away from rapid transit, I believe was cluster one. Yeah, if you want to pull up that map.
Yeah.
Oh yeah, but far away from a rapid transit stop. I noticed, knowing Calgary and being kind of involved in Calgary, that the spatial sort of outline here is almost exactly where the green line is planned to go, the LRT route, and presumably it's planned to go there because there's a lot of existing transit lookups, but maybe the system needs upgrading, right? Needs mode upgrading, both in the southeast and definitely in the north corridor. So I'm curious if you think there's an application here for trying to suss out where transit might be needed, not just from demand, but also from where people are trying to, even though there's existing service, where people are sort of considering it not particularly reliable or confusing or somewhat uncertain.
Yeah, that's actually a really interesting point you made, and I wasn't aware of this probably because I'm not too familiar with Calgary, but knowing that it even kind of makes more sense to data as why that this line is being proposed. And I think I mentioned I do think that it's an opportunity for us to really see where there's sort of a desire for transit and where it's sort of lacking in areas, because presumably you kind of use these tools when transit service is bad or unreliable. So it really gives us an opportunity to see kind of weak points, perhaps.
Very interesting. Thanks.
All right, then we are at the art. So thank you, Lisa, once again for the great presentation. And I wish you, and thank you everyone for joining us today. I wish all of you a great rest of your day.
Thank you.
Thanks a lot.